Now, K-means clustering that we will be applying this week is basically a method that allows you to look at where specific values meet the given clusters that you want to analyze. So if you have 64 clusters that you want in your results, let's say, it will use an unsupervised machine learning method that tries to fit the 64 clusters to given color variations. Each color then is fitted to the given cluster. Colors that are most closest to each other in terms of each cluster are then grouped in that cluster and then returned. It uses unsupervised learning, so that basically means we don't actually tell it which colors will fit where, rather we'll have it try to determine based on the comparison of colors to each other and their differences in terms of the creating for this image, which ones will actually best fit. So it's a standard visualization technique used to effectively use in things like remote sensing, for instance, to find variation in imagery. So if you have a given image and there are something like 96,000 colors, let's say, then it'll try to find 64 colors that are most representative. So in a given cluster, there may be, say, 1,000 or a few thousand colors that are similar to each other. So it may then select one color from each of those 64 clusters and then effectively combine them to create the image. So instead of combining many different colors to create one cluster, it'll take one potential color or one color. The reason why it would do that is, of course, is to be more efficient. So an image with 96,000 colors will be obviously larger and take more time to create, whereas a kind of image with only 64 colors will be smaller but may look very similar to the 96,000 color image. So what this method effectively does is try to find a kind of more optimal way to represent something using a minimal or a smaller number of colors to represent that image. So K-means clustering tells us where those best 64 colors are likely to be found. And then it returns those best 64 colors to then match effectively the image as close as possible, the base image. Okay, and so you can see the explanation here. So it performs a pixel-wise vector quantization of an image. That is, it looks at the pixels and tries to quantify them in terms of the color variation, and then tries to pick the 64 colors that best match the 64 colors that we want in terms of number of clusters. So it reduces the number of colors required, that is the one color that best fits each cluster, to show the image from 96,000 unique colors to 64, while preserving the overall appearance quality. So it tries to keep that quality. So the explanation, as you can read yourself, effectively tries to do what I was saying, which is trying to find an image that has only 64 colors rather than 96,000 colors with minimal number. That is, this minimal number of 64 colors is hopefully a quicker way to represent something that has much more data in it, but in a way that makes it look very similar to that image that has a lot more data. So I'm going to go ahead and run it, and hopefully that'll be more clear. Show you what I exactly mean. So if I run it, if I press Python run, the code should hopefully run. You'll see that it'll quantize, and then it'll begin to create the images, and you can see the image outputs. So this is the quantized image there, the 64 color image, and the base image as well. There's the original image. So this is if you look at figure 1, this is the base original image with 96,000 colors. So it's the sharpest looking one. The quantized image, the ones that uses K-means clustering, is shown in figure 2, and figure 3 shows the quantized random selection. So you can see, hopefully, that the K-means clustering result is actually more similar to the original image. The random selected 64 colors, that is just 64 colors randomly selected rather than clustered and then selected to be chosen for the 64 colors, is actually not as sharp, not as good. The color variation, the shading is certainly different from the original image. So it shows us that by using K-means clustering, we choose an optimal color for each of those 64 clusters and then combine them to create the image. So we basically try to remove that overlap that a lot of colors have. If we randomly select colors, we may, say, for instance, choose 2 colors that don't actually provide the needed variation to represent the base image as close as possible. So that's why this K-means clustering is more effective than the random selection of colors.